Right. So, good afternoon, everyone. Today, we are actually starting off with a theory on vertical projectile motion. I was hoping that we would get a better turnout for this lesson because it actually is going to underpin everything we're going to do tomorrow. Because tomorrow, we are definitely going to start off with some of the questions at 9 a.m. So, if you are attending today's lesson, my suggestion is please attend tomorrow's lesson because it's going to be a good follow-on lesson on vertical projectile motion, and it will also allow you to understand why we are doing this first lesson. Right. So, firstly, this lesson here is going to underpin everything we're going to do. Uh, there's a large amount of work that is actually related to grade 10 work, and there's something about the grade 10 work that we normally don't explain in grade 10 because it's a bit too difficult for learners to grasp. And I'd like to actually let everyone know exactly about how I'm going to do things, because there's a certain way I end up doing questions in vertical projectile motion that's a little bit different from how you may see it done in class. All right, so before we start off with vertical projectile motion, I just want to give you a very, very brief overview about what it is, what you're going to be focusing on, and what are the main aspects, and then we're going to get into the technical aspects of the section as well. So vertical projectile motion is actually an extension of your grade 10 work, where you did equations and graphs of motion. So you can think of this as equations and graphs of motion, but at this time, it's not for an object that's moving horizontally. It's for an object that is moving vertically. So vertical projectile motion, as the name suggests, is basically for an object that is thrown up into the air and basically comes down to the ground. And it sounds very easy. It sounds very simple as well. But the questions can get a little bit tricky and, quite complicated over here. So what I want to start off with firstly is the scenario that we are going to be talking about today. And why am I taking this scenario and what's special about the scenario and everything related to this. So today is essentially a theory lesson. And in this theory lesson, you're going to learn quite a bit about what you did in grade 10, but it's going to be extended so that you have a very clear understanding of where we're going with this. But before we start, let's start off from a place where we should all be familiar with. It's a recap of the grade 10 equations of motion. And one of the big gripes I have about learners in these equations is that they tell me that the equation's on the data sheet and I don't have to learn it. My suggestion is please learn these equations. I'm going to list them. Vf equals Vi plus A delta T. Vf squared equals Vi squared plus 2A delta X. Delta X equals to Vi delta T plus half A delta T squared. And then the fourth one, delta X equals to Vf plus Vi all over 2 times delta T. Now, what's going to change from what you learned in grade 10 compared to this year is the scenario in which you're going to be dealing with it. And as far as scenarios go, I'm going to basically outline one of the more complicated scenarios. That scenario is where you have a tall building, and what you are going to do is you're going to throw something off from the edge of this tall building, and it's going to go up into the air, and it's going to come down to the ground. So the object is going to actually do this in the air. I'm going to put this in gold so you can actually see what it's doing. It's actually going to go up into the air. It's going to go straight up, reach a certain maximum height, and it's going to come straight back down along the same line, miss the edge of the building, and come down to the ground. So essentially, that's what the object is going to do. Now, to be quite honest, if you had to look at this diagram in a past exam paper, you will never see it drawn like this. Actually, what I'd like to do is, before we get into the questions, I want to give you an example of what you will actually see in a past exam paper in terms of a diagram, so that you are fully aware of what it is really doing as opposed to what we're going to draw for you in the paper. If they don't show it to you there. Maybe we'll get lucky here. No, it's another hot air balloon. I'm looking for one where we have an object that is released from the edge of a building. Last one, if we get lucky, it's good. If we don't, I'm just going to abandon this. All right, so they don't show it to you. So if they had to draw the diagram for you, you're going to find that the diagram is going to look something like this here. In reality, the object never does that. In reality, we are dealing with an object that's going to do this. But you will never ever see a diagram drawn like this for the path taken by the object going into the air. In reality, this is what the object is going to be doing. And that's the reason why it's called vertical projectile motion. The reason why it's called vertical projectile motion, and the emphasis here is on vertical, is because the object is going to go straight up vertically and come straight down along that same path, which means the only direction in which the object is going to move is strictly along the y-axis. And because this object is going to move along the y-axis, those delta x's should change to delta y's. Now in your matric paper, you'll find the delta x and the delta y version of your equations of motion given. We generally use the delta y versions when we're dealing with vertical projectile motion. So vertical means that the object goes straight up and comes straight back down as if it is moving along the y-axis. I'm going to explain what a projectile is later on. And I want to talk about now strictly about the motion of these objects. When this object is moving, there are three vector quantities that we must pay careful attention to. And we must not confuse them with something that we are used to in our daily lives. The three vector quantities that I'm going to talk about today is sitting in these equations. It's velocity, which is in quite a few of the equations, as you can see. The next one is the delta y itself that I was telling you about. And the last one, which is technically the most important one, but it's the easiest one to deal with, is this acceleration here. Now, this acceleration is not just any acceleration. This acceleration is the acceleration due to gravity that will be present on our planet, which is Earth. In other words, it's going to have a set value, and I'm going to show you why it is that set value when we actually deal with the questions. So what we're going to deal with now is this scenario here. So firstly, why take this scenario? What's so special about it? It's actually one of the most difficult scenarios. It's a scenario where we can analyze change in position, which is your displacement, your velocity, and your acceleration in great detail. And if you understand how this scenario works, then you can understand any scenario. The problem is, if you start learning this the wrong way in school, and I'm not saying your teacher is deliberately going to do it wrong, right? You may understand it from your teacher incorrectly, right? And you use something incorrect. It's going to make some of these easy questions very, very difficult to understand. Actually, I've seen a learner take a 3-mark question and do an entire page of working for the 3-mark question because he just simply didn't understand what the concept meant. So you need to understand these concepts before we actually deal with them. So we're going to deal with today the vector nature of velocity, displacement, and acceleration for an object that is thrown off the edge from a tall building. I'm actually going to put up all the videos for this because I know that no one in this group is actually taking charge of the videos. So these video links are now going to be sent to a grade 11 group. And they're going to create a YouTube channel for all the videos. Why? Because these grade 11s are going to learn the grade 12 work with you. And also, they're willing to obviously just do it. Right? So this first lesson here, you may want to go back to it. Because eventually when the questions get really difficult, you may want to understand what happened or what did I miss in the first lesson. Now, something about this section here. It's unlike momentum, where momentum had different parts to it, which was what is momentum, what is impulse, impulse momentum theorem, conservation of linear momentum, elastic and inelastic cohesions. Here, it's basically equations and it's graphs. And there's different scenarios. There isn't tons of theory. But what is difficult is the application of the theory. And the theory becomes difficult to apply when you don't understand it properly. So before we start, I want to explain something about this building problem that you're going to see me do. And I want you to understand why we're doing this as well. So we're going to have the same building. But apart from Michaela, anybody else has already started with this section?
We started with it in school.
Who's that?
Ismail Adam, G.
Okay. How far y'all gone, Isma?
We basically finished the section, sir.
Okay, how many lessons?
It was about 4.
All right. Okay, so I wanna just be quite honest with you. So during the course of this week here, I'm not gonna put up a poll and check whether you are available or not. If I can, and I have the strength and you wide awake, I'm going to call you up and I'm going to ask you to just join me for half an hour slots to finish up as many different hours as I can to do many different scenarios. It's not going to take me 4 hours. I'm going to be quite honest with you. It's quite likely going to take me at least 10 hours. And by the time I hit the 10th hour, I'm going to be quite likely towards the end of the first week, in the middle of the second week. So it's not going to be a short journey. And there's many reasons for it. And I don't want to rush the section because it's one of those sections that I know learners hate. So firstly, what am I going to do with this sort of diagram here? You're going to see me change it a bit. I'm going to end up drawing this diagram like this. The object is actually not going to be doing this in the air. It's going to go up. It's going to come back down to its starting position. And then when it comes back to its starting position, it's going to go downwards and it's going to hit the ground. But this here is a very inaccurate representation of what it is really doing. It's actually doing that. Can anyone tell me why you will actually see it drawn like this in a class sort of example or in an exam paper? If you've done this section, you would have seen this diagram quite often. Anybody knows why you see it like this, although in reality it's actually doing this here? It's got nothing to do with physics, by the way. Anyone? Because here it's easy to see where the object is going up, where it's going down, and where it's gone below the starting point. Here, it's a bit of a cramped diagram. And technically, this up and down motion here is on top of each other. And what we're going to be doing now is we're going to be analyzing these three vector quantities. How does displacement change when the object goes up into the air, comes back down to its starting position and goes below its starting position? How does velocity change? How does acceleration change? Now, for some of you that have finished this section, and I mean, some of you have already basically are done with it, right? You've already learned how to work with certain equations. So the difficult part would be to try and undo what you've learned, or hopefully to reinforce the correct way that you've supposed to learn it. I want to tell you also something about the way we're going to do this. You're going to basically unfold this whole section as you would do it at university level. So when you go to first year university, in the first 2 or 3 weeks, you're going to do vertical projectile motion again, and you're going to do it in exactly the same way. There won't be any difference, right? There's one added complexity which you will learn about, which is called 2D motion, right? We're doing what we call 1D motion. 1D means motion in one dimension, right? But you'll do 2D vertical projectile motion. But the theory will be basically the same that we are doing here. Right. So what do I mean by let's analyze velocity, displacement, and acceleration? I'm going to start off with the definition of displacement here. And it's a very simple definition, but I don't think it really tells us what displacement is. The definition of displacement is change in position. And I find this to be very vague. Actually, when I was in school, the definition of displacement was completely different. And I thought it was a far better description of what displacement is than this very, very vague definition. So when I was in school, the definition of displacement was the straight line path from the beginning to the endpoints of a journey. Let me repeat that. Straight line path from the beginning to the endpoints of a journey. So we're going to see an object that is thrown up into the air, and we're going to see the journey that is unfolding as this object is going up into the air. And we're going to start off with displacement. Now remember, the object is actually going straight up and coming straight back down, but you're going to see it look like this here. If you remember that at the back of your mind, you'll be able to tell me a whole lot about these quantities. Right, so what you're going to see is actually uh, a motion guided PowerPoint. That means it's not a static PowerPoint. It's a PowerPoint where things are going to be changing on it. And what we're going to be analyzing is basically a ball that is going to be thrown off the edge of the building and it's going to come back down to the ground. But what I want to just emphasize again is what's special about this ball is that this ball is actually going to be going straight up and it's going to be coming straight back down along that same path, missing the edge of the building and coming down and hitting the ground there. You are not going to see this happen. You are going to see us draw it like this here for the up part, coming back down to the starting position, and then going below the starting position. You're going to see us do that. The reason for the exaggeration, it just makes the analysis very easy. We're going to be analyzing three basic quantities over here, which is going to be displacement, velocity, and acceleration. And this is the most important thing. You're going to see me do this in every question. So whether it's an easy question or a difficult question, I'm going to take all upward pointing vectors to be positive. So whether it's going to be question 1 or question 30 down the line, all the vectors that point upwards are positive, all vectors that point downwards are negative, and that's what we're going to do in every question. What I do find is that some schools change the convention to suit the question. So here we're not going to be doing this at all. It's going to be the same convention for all the questions. There's no air resistance. When there's no air resistance, something very special occurs. And the quantities we're going to analyze are displacement, velocity, and acceleration. I don't want to make this a boring PowerPoint, so this is what we have here. Displacement, according to my definition, straight line path from the beginning to the end points of a journey. There we have a ball that is thrown up into the air and it's coming back down to the ground. What I'd like to talk about is what we have here at the beginning and what we are analyzing here. So don't think of this as a graph, please, because this is really not a graph. We are actually going to be putting in our building over here. So let's assume that that's where my building is. And this here is time t equals to 0 seconds. Now remember, the ball is not doing this in the air. The ball is going straight up and coming straight down. That's 0 seconds, that's 1 second, 2 seconds, 3 seconds, 4 seconds. At 5 seconds, the ball is there. That's 6 seconds, 7, 8, 9, 10, 11, 12, 13. And there's our building at the beginning. You're going to see the building disappear now because this part is going to come out and then we're going to talk about the vectors. You're going to help me. This is our starting position. And each second that passes will be a typical end position. I want to talk about these end positions here, where I'm calling it E. For 1 second, the ball is not really there. The ball is actually here. For 2 seconds, the ball is not there. The ball is actually here. For 3 seconds, it's not there. It's there. For 4 seconds, it's here. For 5 seconds, it's right on top there. Remember, we said that this object is going straight up and it's coming straight back down on that same line. We've drawn it out like that so that you can see the vectors clearly. Now, what's my displacement at 0 seconds? Anyone? It's an easy answer. Anyone can get it. What's my straight line path from my beginning to the end point at the very beginning? It's 0, everyone. There's no displacement. Here's my displacement vector after 1 second. It's pointing upwards, and it's a small positive value there. That's 2 seconds, 3 seconds, 4 seconds, 5 seconds. Can somebody describe the displacement vector for 6 seconds? Let's use the word up, down, bigger, smaller. If you've completed it, you should be able to give me the answer. Come on. I'm going to define displacement again. The straight line path from the beginning to the end points of the journey. Your beginning is here. There's your beginning here. These are all the different endpoints. That endpoint there, where it is 6 seconds, is in fact here, on top of that other blue one now. Can you describe the displacement vector now? Anyone? It's exactly the same as 4, because this is where you started, and that's where you ended. So there's your displacement vector for 6 seconds. So your displacement vector for 6 seconds will be this vector. Your displacement vector for 7 seconds will be there. Your displacement vector for 8 seconds. For 9 seconds. And for 10 seconds, what's my displacement? Anyone? I'm back at the starting position now. Correct, it's 0. These are all positive displacements. Increasing positive, and then decreasing positives to 0. So when do you get a negative displacement? You're going to get a negative displacement anywhere below your starting level. Because this 11 seconds here is in fact here. The 12 seconds there is in fact here. And the 13 seconds is right here, just before it hits the ground. So what's my displacement for 11 seconds? There's my displacement for 11 seconds. For 12 seconds, for 13 seconds. And these are all negative. I want you to look at the vector for 13 seconds there. And I want you to have a look at the length of this vector here. Sorry. The length of this vector here. On the height of the building. the length of that vector and the height of the building is exactly the same. So if this building hypothetically was 20 meters, then this displacement vector at the end is minus 20. So if somebody asks you what's your displacement after 13 seconds when this object is hitting the ground, when it's hitting the ground over here, the displacement is minus 20. Many learners think that your displacement at the end of 13 seconds is everything that you did from the beginning right to the very end. That's not true. Displacement is simply from the beginning, straight line path to the end. It's not the actual journey. What the ball actually does in the air, that's your distance. What you have in your formula, your delta y, that's your displacement. Don't confuse your displacement with your distance. So if you continue here, it's decreasing displacement to 0, then negative displacement, and that last vector that we have at the end there, that last vector at the end, that there is actually equivalent to, so let's see something. That last vector there is equivalent to the height of the building that we had at the beginning. That's very, very important. That your displacement at the end is the same as the height of the building that you had. So if they told you that this ball took 13 seconds to reach the ground, then your displacement at 13 seconds here is the negative of the height of the building. Now, very few learners actually understand that. That's one of the reasons why we've taken the time here in this lesson to actually explain this, so that when we actually do end up doing the difficult questions, you actually understand it a bit better. The next set of diagrams is for velocity. Now, you already know how velocity works. Velocity is the only vector that changes direction when the object physically changes direction in the air. What does that mean? It means that if the object is going up, then your velocity vector is upwards. If the object is going down, then your velocity vector is downwards. Now, if you go backwards to displacement, you're going to find that although the object was coming down in the second half of the journey, your displacement vectors were still upwards. So here's some common mistakes about velocity. Again, for velocity, we're going to have our building here at the beginning. And at t equals to 0 seconds, we're going to have an object that is thrown off the edge of the building. That's 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Again, same 13 seconds. But now we're not looking at how high or how far it goes with respect to its starting position. We're looking at the exact velocity of the object. Anybody wants to comment about the velocity at t equals to 0 seconds? Because this is a big problem with some learners, which is the initial velocity here. Anyone? Anything you want to state? Remember here, the object is going to be going up. It's going to be going upwards from 0 to 5 seconds. So all these velocities from 0 to 5 seconds are going to be pointing upwards. All the velocities after 5 seconds, because the object is coming down, all these velocities here are going to be negative. Velocity is the only vector that changes direction when the object physically changes direction in the air. Now, many learners think that that is true for all three vectors. It's only true for velocity. Let's talk about the initial velocity there. The people that actually did this section, you should be able to tell me something. Tell me anything about the initial velocity when an object is thrown up.
At 5 seconds, the velocity will equal to 0.
Good. Okay, let's put that down. Your velocity is not 0 at t equals to 0. Your velocity is 0 only at the highest point. We'll explain why just now. So I want to give you the exact values of the velocity from 0 to 5. You won't know this, obviously, because you haven't been doing it long enough, but I can tell you what it would be. The exact value of your velocity, if you took 5 seconds to go up, at t equals to 0 seconds here, the exact value of the velocity would be 49 meters per second. At 1 second, the velocity here would be 39.2. It would be 29.4. It would be 19.6, 9.8, and then 0. Those velocity vectors will all be pointing upwards, but those would be the exact values. Let me write it down for you. 49, 39.2, 29.4, 19.6. You're not expected to know this, by the way. 49. Oh, I did it wrong. Let me go back. 49, 39.2, 29.4, 19.6, 9.8, and as somebody pointed out, it's 0. These are all positives. All these velocities are positives. When it's coming down and it's in the same displacement position that you had previously. In other words, your displacement at 4 seconds and your displacement at 6 seconds, by the way, is the same. They're both upward pointing vectors. For those of you that have forgotten, you want to go back and watch the video. But the velocity is not the same. Your velocity at 6 is an increasing velocity vector in the opposite direction. 9.8, 19.6, 29.4, 39.2, and here, right back at the starting position, it's 49 in the opposite direction. So that there, minus 9.8, minus 19.6, minus 29.4, minus 39.2, minus 49. Here, it's minus 58.8. And you can go down the line. It just gets larger and larger and larger. I want to talk about the final velocity there. Now, when I was in school, I thought that the word final velocity meant the velocity after it hit the ground. Actually, not true, because the velocity after it hits the ground is actually 0. There's no velocity. Your final velocity is the velocity at the instant at which it touches the ground. In other words, just before it penetrates into the ground and comes to rest. You're going to have your largest velocity at 13 seconds, by the way. It's going to be larger than any of the others. And it's going to be a negative as well. So if I take all of this out now and show you what the velocity vectors will look like, it was exactly what I told you. 49, 39.2, 29.4, 19.6, 9.8, 0, minus 9.8, minus 19.6, minus 29.4, minus 39.2, and at the same level at which you started off, you're going to have the same magnitude of velocity, but in the opposite direction. In other words, if it's plus 49 here, it's minus 49 there. If it's plus 39.2 here, it's minus 39.2 there. In other words, at the same displacement position, you have the same magnitude of your velocity, but it's in the opposite direction. That's 29.4. That's minus 29.4. You don't have to worry how I got these values. Now, once it goes below the starting position, the velocity just gets larger and larger and larger. And when it's about to hit the ground, you will find the largest negative velocity. So what you need to remember here about velocity is that because we're taking upwards to be positive, all your velocity is pointing upwards represents upwards motion as well. All the velocity vectors pointing downwards represent downward motion as well. So I don't want to use a pencil. I want to use my pen. As it goes up into the air, the velocities are all positive and decreasing to 0. When it comes downwards, the velocities are all negative and it's increasing up to the point it reaches the ground. Now we are going to talk about those exact values I put down, because from those values, we're going to get to acceleration. These are not thumb suck values. These are the exact real values from 0 seconds to 1 second, 2, 3, 4, 5 seconds. If you're wondering how I know this, I've done this many times before, so it's a bit easier for me. If you've done hundreds of problems, then you would also figure the same thing out eventually. Right. I want to show you how we get acceleration. Acceleration is simply a derivation from velocity. In other words, if you know your velocities, you can get your acceleration. Because acceleration is the rate of change of velocity. It's your change in your velocity over your change in your time. I'm going to work out my acceleration for the first 1 second here. Just that 1 second. My final velocity is 39.2. My initial velocity is 49. And my difference in time, my change in time from there to there is 1 second. You plug that in on your calculator. There's the minus 9.8 cropping up. You can try it for any other 1 second interval, or even 2 second intervals if you wanted, or 3 second intervals. You'll get the same thing. For the next second, 1 to 2, you'll get the same thing. I'm going to take another random one. The time interval from 2 to 3 seconds is still 1 second. My final velocity is 19.6. My initial velocity is 29.4. My change in my time, where the velocity was 19.6 and 29.4 was 1 second. If you work that out, you'll get minus 9.8. Some of you may be wondering, but you didn't do anything on the other side? All right, let's talk about the other side. When the object is coming down, all these velocities are negative. And again, there's a peculiar way it changes from the 5th to the 6th, 6th to the 7th, 7th to the 8th, 8th to the 9th, 9th to the 10th. I told you at the same displacement position, you're going to have the same magnitude, but the opposite direction. Minus 9.8, minus 19.6, minus 29.4, minus 39.2, and minus 49. Before we get towards the end of this lesson, allow me to just take a sneak peek. Oh, my apologies. In my zest to well, let me just go for the second half there. Quickly do that for you. So there's my velocity. Right, let's go for it. So that's 6, 7, 8, 9, 10 seconds. Minus 9.8, minus 29.4. The time difference between 7 seconds and 6 seconds is 1. My acceleration, my final velocity, minus my initial velocity, and 7 minus 6 gives me 1. Minus 29.4, minus 9.8, all over 1. You can try it. You're going to get minus 9.8 again. If you take it between, say, 9 and 10 seconds, minus 29.4. Oh, sorry. See, no one's paying attention. That's supposed to be minus 19.6 there. That's minus 29.4, minus 39.2, minus 49. If you try it between 9 and 10, and do the acceleration again, minus 49, minus 39.2 over 1, you're going to get the same acceleration. That's my point. Whether the object is going up into the air or coming down, that acceleration is always pointing downwards. So you may be wondering how come it's downwards. The answer is very simple. These objects that we are going to be dealing with that are in the air have only one force acting on it, and that's the force of gravity. When the only force acting on an object is the force of gravity, then we say that the object exhibits projectile motion. So projectile motion simply means that the object has only one force, which is the gravitational force. The gravitational force acts downwards. From Newton's second law, the acceleration is in the direction of the net force. If your net force is downwards, that means if your gravitational force is downwards, then your acceleration is going to be downwards as well. That's why the acceleration is pointing downwards all the time. Whether the object is going up or coming down, the acceleration due to gravity is downwards, and that acceleration due to gravity doesn't change because your gravitational force doesn't change. So whether the object is going up or coming down, your acceleration vector, which is the last vector now, and I've drawn this randomly to show you, you could take any point, even at the highest point of motion where the velocity is 0, the acceleration is downwards. Now, you may want to go over this video again, because tomorrow I'm going to use everything that we did from here to start off the first type of question we're going to deal with. And that's simply to check to see whether you understand the convention that I'm going to use. I'm not going to use any other convention but the one we've shown you here. And what is the convention again? Just as a very, very quick recap in under 5 minutes. Here's your displacement vectors. At t equals to 0, you got 0 displacement. From 1 to 5, your displacement increases to a maximum. It's pointing upwards and it's positive. From 6 to 10 seconds, the displacement is still positive, but decreases to 0. When the object goes below its starting level, then your displacements are all negative. Velocity. At the start, you have your maximum positive velocity there. Your velocity decreases to 0. At the highest point, it's 0. And it changes, by the way, by 9.8. That's how I knew all the values. From 49 to 39.2, there's a difference of 9.8. From 39.2 to 29.4, the difference is 9.8. That's what 9.8 meters per second squared means. The change in velocity per second is 9.8. Negative 9.8, negative 19.6, negative 29.4, negative 39.2, negative 49, negative 58.8, negative 67.2, and 78. That was 68.4 and 78.2 there. Those are your velocities. Your acceleration, whether the object is going up or coming down, the acceleration is always going to be minus 9.8 meters per second squared downwards. Whether the object is going up or coming down, for the most complicated motion where an object is thrown off the edge of a building. Thank you, boys and girls. We're going to be using this tomorrow. This video will be put up. I'm going to send you a link for the video once it's up. And if you want, you can watch these videos again. Right, 9 a.m. tomorrow, we start with the questions.